Okay, let me move it away from my way. So here's what I have. You guys have this one right in front of you. I apologize, I wanted to make a copy, a colored copy for you. My badge is not working this morning, so let me just walk you through what we have and what we need to achieve. As electrical designers, guys, you will be required to size the riser. This is called a riser, a one-line diagram. As a matter of fact, I think Hallberg is coming at 9 o'clock to talk about exactly the same thing. How do you size a riser or a one-line diagram and draw a riser or a one-line diagram? So this is directly related to Hallberg. I hope I can finish by 9 when they come, guys. Here's what we have. We have the electrical utility. The red is the power line. We're coming from Xcel Energy, bringing power into a panel that we're calling SP service panel, exactly like you guys are doing. From that service panel, we're taking chunks of power. That's what the riser is. They chunk the power, chunk. One chunk is to feed a panel that's called the receptacle panel. Does that sound familiar, Derek? Is that what we do for a commercial project? Another chunk is to feed the lighting panel. Isn't that what you guys are doing with chat? Lighting panel, receptacle panel, main panel. And to add salt to injury, I added a mechanical panel. MP is my mechanical panel. That's typically what they do, guys, when they have a riser. They have a main panel for most of the buildings. And then from that main panel, they take a big chunk of load and they put it in a panel called a receptacle panel. Another chunk of load, they put it on the lighting panel. And a third chunk of load, they put it in the mechanical panel. So anybody can guess what's in the receptacle panel? Receptacle load. Anybody can guess what's on the lighting panel? Lighting loads. How about what's the mechanical panel? Mechanical panel, guys, has all the mechanical equipment, heating, cooling, and ventilation. Cool? In our project, I want to remind you guys, we do not have a mechanical panel because we're feeding our mechanical equipment directly from the main panel. Cool? Okay, so what we need to size is the following. We need to size the following. Number one, we need to find the size of the service panel as well as the size of each and every one of these three panels, receptacle panel, lighting panel, main panel. Then we need to size a service conductor, that's number three, the service conductor coming to the main panel. Then we need to size the feeders going to each and every one of these panels, that's 3, and the overcome protection device ahead of it. Isn't that what you guys doing with me? You're sizing the feeder and the overcome protection device ahead of it. Then we need to size the equipment grounding conductor. Can you guys see that number 4? The equipment grounding conductor for each one of these panels. Number 5 is the main bonding jumper at the service. We take the neutral and the ground and we bond them together. And number 6, Karen, is going to be the grounding electrical conductor. Can you guys give me, I need a thumbs up that we fully understand what we're trying to achieve here. Adam, Brian, good, Karen. Okay, so that's what we're doing. We have 4 panels and you guys, our project has only 3, right? The main panel and 2 lighting receptacle. I added 1 more because that's what we typically have in the riser. And we are to size the feeders and overcome protection device for them, the service conductors and overcome protection device, service disconnect means or overcome protection device, the main bonding jumper and the grounding electrode conductor. The main bonding jumper right here, the grounding electrode conductor that goes to the rod, to the pipe, and the equipment grounding conductor in every one of these panels. This building is an commercial office building. It's a 50,000, does that sound like 50? This is 5, believe it or not, 50,000 square foot. I'm telling you, you're going to do that one for a 50,000 square foot commercial building. Doesn't matter how many stories. The voltage is 28123 phase 4-wire system. That's what we chose for this system, for this voltage. Could I have chosen different voltages? Yeah. Would the calculation be different? Absolutely not. Same calculation. If the voltage was 480 or 288 or 120, obviously if it's single phase, you don't use the multiplier for the single phase. One more time, before we leave this screen, everybody understand what we're trying to achieve? Okay, shall we go ahead and achieve that one? Cool? Okay. So you guys have it right in front of you. Okay, now, I want to correlate the sheet that I gave you guys with that one. I should have done them in the same format. I want to be just numbering a few things in, let me use color blue. I want to use blue just to kind of emphasize what we're trying to achieve here. So for the receptacle, the sheet that I gave you, the Excel sheet, guys, the receptacle, I'm calling him A here, calling the receptacle A. In this sheet that I gave you, anybody knows what the receptacle was called? It's called number 1. So I'm going to go, how am I going to do that? I'm going to say number 1 here. Everybody understand why I put number 1 here? So number 1, correlate with the sheet, the Excel sheet that you guys have. Okay, correlate with the Excel sheet that we have. See, I changed the Excel sheet before I did this presentation. So let's go ahead and, so here you go. So the first number 1, can you guys see that? Here's number 1. Number 1 at the top talks about receptacle. Receptacle. Cool. That's number 1, receptacle. All right, so let's go. So it correlates with the stuff that you have. Number 1 is receptacle. Okay, so I do have 500 receptacles at 20 amp and running at 120. That's a receptacle that I have. 500 receptacles, they're all 20 amps at 120. Cool. Then I have a multi-outlet assembly. Multi-outlet assembly. Can you guys see the multi-outlet assembly? The multi-outlet assembly will be 1.1 in your sheet. 1.1. That will be a 1.1 in your sheet, the Excel sheet. Multi-outlet assembly, I have simultaneously used 80 feet and non-simultaneously used 60. Everybody understand how to read my chicken scratches sometimes? Okay, so that's your multi-outlet assembly. Any question, guys, about multi-outlet assembly? Okay, these are correlated to 1 and 1.1 in your sheet. Okay, let's keep going. Lighting. I have 300 lights. 300 lights in this building. Each one of them is burning at 1.65 amps and they're burning at 120. These are the lights that we have in this building. Cool? I'm giving you this information. Now the lights correlate in our sheet, general light, let's go general lighting, that will be 2. This one will be related to 2. B will be related to 2. Can you guys write next to the 2 so it relates to that sheet that we have? Okay. So that's my lighting, 2. Then show window, my track light, I don't have, show window. Show window, I have 40 feet of show window. This is related to 2.6. That was in our sheet 2.6. In our sheet it was 2.6. And then I have track light. Track light is 2.4 in our sheet. This is the track is 2.4. The track light is 2.4. I have 100 feet of track light. Sign, my sign in our sheet was 2.5. This sign was 2.5. Okay. And parking lot, what was the parking lot? Parking lot was 2.7. Parking lot was 2.7. Okay, that's my parking lot. Parking lot, I have 6 fixtures, 400 volt amp each at 120. I need thumbs up that we fully understand what we're given for this commercial building. Starting from Brian. Does it make sense, Brian? Yeah. Karen? Derek? Good. Adam? Matt? Okay. So this is a commercial building. These are the information in it. And you guys are supposed to size that riser, all the riser for it. The reason why I put these numbers here so it correlates to the sheet that you guys have. Please write these numbers on your sheet. Write these numbers in your sheet. It helps you correlate how the calculation is going to go when you do your math. Any question about the given? Okay, so no questions about the given. Let's go to heating. My heating is related to 4. That was 4 in our sheet. 4 heating and cooling was 4.1. The cooling was 4.1 and the heating was 4. The way we did it, right? Heating and cooling. For heating, I have 3 15 kW heaters, 208 3-phase. And for cooling, I have 3 chillers. Each one of these babies are running at 82 amps at 208 3-phase. These chillers. Cool? These are my chillers. Motors. For motors, guys, we have the for motors that will be step number, which step? 4.4. For motors that will be a 4.4, step 4.4. For motors, I have an air handling unit, two air handling units, 20 horsepower each at 2A 3-phase, and a pumps to pump water. Two of them, each one of them is 10 horsepower, 2A 3-phase. These are given in this building. Any comments, guys? Any questions? Comments, questions about that? Comments, questions? Make sense? Everybody can see that? Kitchen equipment. Where did we put kitchen equipment? Kitchen equipment is number 3. Kitchen equipment in our sheet was number 3. So stick number 3 there. For kitchen equipment, I have a water heater, 3 of them, 5 kW 2A 3-phase. Dishwasher, 3 of them, 2 kW. Range, 3, 10 kW. Heater booster, 3 kW 2A single phase. Some of them are single phase and others are 3-phase. It's so important to know what's single phase and what's 3-phase, because that when we size the neutral, guys, they're not going to count towards sizing your neutral. These will not count towards sizing your neutral. Any comments, guys? Any questions? Any comments? Any questions about that? Comments, questions? Okay. Everybody understand what we have on this sheet? Okay. So let's go ahead and start doing the calculation. Let's go ahead and start doing the calculation. The first thing we need to do, guys, from article for receptacle 220.14K, it will tell you the following. For receptacles. A1, I call it A1. A1 is equivalent in our sheet. A1 in our sheet, choose the largest unknown receptacle for office building. Okay. A1 is equivalent to 1.4. This one is equivalent to 1.4 in our sheet. This step is 1.4. From the NDC code book, guys, it will say that you need to take 1 volt tab, multiply that 1 volt tab by 50,000 feet, and that will get you 50 kVA coming out of this 50 kVA for the residential, for the commercial building. So this is step 1.4. These are 1 volt ampere square foot from the NEC code book for a commercial building. Okay. This step is 1. That's 1. NEC 220.14, I will tell you guys, for every receptacle that you have in your building, we call it actual. For actual, the actual stuff that you did, 500, anybody knows what 500? Because we have 500 feet. We have 500 receptacles that we install in this building. Each one of them will be at 180. 500 receptacles, each receptacle will be at 180. By the way, this guys will be your test number 1, just FYI. This information will be on the test number 1 that we're going to be taking. And when for the test, because there's a lot of information, my expectation, guys, will write these rules on a cheat sheet, bring them to the test. It doesn't hurt my feeling, because there's a lot of info. Okay, so your actual 500, if you multiply this one, will give you 90 kVA. 90 kVA. 90 kVA. That's your actual. Then you go to the multi-outlet assembly. Your multi-outlet assembly was 1.1. This was 1.1. The multi-outlet assembly. 1.1 in the sheet that I gave you. 1.1. For multi-outlet assembly, guys, there's the simultaneously used. The simultaneously used ones, we take 60 feet, divide them by 1, because multiply them by 180. Because the code in 220.14H says if it's simultaneously used, you give 180 for every 1 foot.
Simultaneously was 80.
Or did they flip them? Simultaneously was 80. Okay, if they are non-simultaneously used, simultaneously was 80. So I flipped them here. Ouch, Chad. Okay, can I go back? It's easier to fix that one because all my math is based on this. I'm sorry, guys. Let me just go one step here. Can you flip these? Thank you. So no, I know because my calculation is based on. I don't want to do the math. I'm just lazy to do the math. Just do this 60 and 80. Flip these. This becomes, can you guys make this is 60 feet and this is 80 feet? Cool? Okay, can you get flip these on that one? Thank you. One of us is awake. 60 and 80. All right, so simultaneously used, which is the 60. We do the math on that one. When you guys do the math on that baby, that will get you 10.8 kVA. 10.8 kVA. 10.8 kVA.
And just make sure where the 180.
The 180 is coming from 220.14H. It will tell you if it's simultaneously used, you give 180 volt amp for every 1 foot. Non-simultaneously, if it's non-simultaneously, you take the 80, divide them by 5, why 5, multiply by 180. If it's non-simultaneously used, guys, 220.14H will tell you for every 5 feet, give 180 volt amp. For every 5 feet, give 180. So you take the 80, divide them by 5, and that will get you 2.9. 2.9 kVA. 2.9 kVA. 2.9 kVA. This step, guys, A2 and A3, this will be equivalent to 1.2. Here is 1.2 when you add them up. In your sheet, this step here is equivalent to 1.2. You add them up. So you're going to add A2 and A3. You're going to add A2 and A3. So A2, I have 90. Okay, so you're going to add all this. We're going to add the, okay, I see what we did here. We're going to add the 90, the actual, K, plus these two, the 10K, 10.8K, plus the 2.9K. When you guys add them up, it's going to add up to 103.7 kVA. This is step 1.2 in your sheet. Step 1.2 in your sheet. You add them up. You add the simultaneously, non-simultaneously with the actual. With the actual. Any question, guys, about the calculation for? Derek, does it help when I put these where it correlates with the sheet that you guys are designing? Because when you're doing the math in Excel now, look at the math that we did here. That's the math that you're looking for. That's the math that you're looking for. Okay, Brian? Make sense? Like I said, guys, test number 1 will be a problem, a commercial building, and you're supposed to size the stuff for it. So be aware, we're doing this one for 2 reasons, Derek. 1, for our project, and 2, because also you're going to be tested on it. So just you know. Okay, then this step, guys, is equivalent to the demand factor. Where did we put the demand factor? General lighting, 220.44. 220.44. That was equivalent to applying the unknown. We didn't do the unknown general. Okay. For office building. Okay, here you go. 1.3. This is equivalent. This step is equivalent to 1.3, guys, in your test. 1.3, where you apply load demand factor for non-dwelling. Okay, so for non-dwelling, you take the. So what you need to do is from table 220.44, you're going to take 103.7K. The first 10K kVA, leave them alone. The remainder, which is 103.7 minus 10K, multiply this by 0.5, and then add them up. One more time. You're going to take the first 10K, leave them alone. The remainder, which is 103.7 minus 10, multiply them by 0.5, and then add. Then you're going to add them up. When you do this step, you will end up with 56.9 kVA. 56.9 kVA. Any comments, any questions, guys, about applying the demand factor for receptacles in a commercial building? Demand factor for receptacles in a commercial building. This step is 1.5 in your sheet. And thank you, it's, where's the largest of demand NEC, choose largest of, is largest EST, right?
Yeah.
I don't know why I always write it IST. Did they change them lately? Does it used to be I and then they switched it to E lately? Yeah.
I could get 56.9, and I got 98.
Okay, take 103.7 minus 10
3.7 minus 10.
times 0.5
I get 98.7.
times 0.5.
Yep.
What type of math are you doing here?
103.7.
103.7 minus 10 equal times 0.5. Where do you get that? I get 46.85 plus 10. Get you 56. I think you did something wrong.
You put 107 minus 10 times.
No, first you subtract them, then you multiply by 1.5.
103.7 minus 10 equals 93.7 times.
Yep. Yep.
46.85.
Plus 10.
Oh, that's 10, okay.
You got it. Plus 10. This is the math that you guys need to do at step 1.3. That will help you do when you do the math. That's the math I'm going to do in step 1.3. Okay, then step 1.5, we will tell you choose the largest of demand, NEC, largest of demand or NEC, or demand or NEC. Basically, the demand that we did here or the NEC. So the largest of these two steps, my friends, is going to be the largest would be the largest of these two numbers, basically 50K VA or 56.9. The largest of these, obviously, is going to be a 56.9 kVA. That's the one. Can you guys highlight this? That's the one that you're going to carry with you downstream. That's the one that you're going to carry with you downstream. Any comments? Any questions? So you need to do the largest of the two. The largest of the two. Comments, questions? Make sense? Derek, any questions before we leave this step? That's so in 1 point, I can't emphasize guys when I say 1.3, 1.5. I hope this will help you when you design your sheet to know what the math is going to be there. Okay, shall we flip to lighting? Karen? Flip to lighting, yes, no? No? Brian? Good? Derek? Good? Okay. Okay, step number B, lighting. So we're done with the receptacle. That's a demand for all the receptacles. I can't emphasize. Could you please put it between like stars here? Because that's a number that you're going to be carrying downstream. That's why I highlighted it. It's going to be carried downstream. Okay, for lights. We talked about lights, guys. Lights. We have two for lights. We have the actual and we have the general. So the actual light for office building and banks, okay, choose the smallest of, okay, so we have two general light. I'm trying to demand is choose the largest. And the C code book for actual light, guys, use 3.5. So we're going to be using for this one 3.5 multiplied by 50K because that's the square foot of this building. And don't forget to multiply it by 1.5, multiply it by 1.25, and that will get you the continuous load, which is 21,219 kVA. That's your continuous load. Then the actual, your actual, guys, is 300 fixtures multiplied by 1.65, each one of these fixtures, multiplied by 120, that's the voltage, multiplied by 1.25 because it's continuous load, and that will get you 74 kVA. One more time. Can you guys see that? First, you find the NDC code book, and then you find the actual. Let me put the numbers on them. General light. This one will be 2 in your code, and total general lighting load. And this will be 2.1. This will be 2.1. So this is 2.1 in your sheet. So important because it correlates to the sheet that you guys have. Okay. Lighting demand load 220.42 guys give you a demand load lighting of 100. So you don't do anything with the light. The demand load you don't cut it. If you go to 220.42, you don't cut it. Then choose the largest. This is step 2.2. It says choose the largest. I don't know why I have largest. Choose the largest of the two. Choose the largest of the two. Choose the largest of these two. 74 kVA. And the other one is 219 kVA. You are to choose the largest between 74 and 219. It doesn't take genius to say 129 kVA is the largest for this step. And do me a favor, put two big stars next to it. I can't emphasize, that's a calculation that you are to do, guys, under B. B is lighting, math. The 2 and the 2.1 and 2.2 will help you hopefully correlate with the math that's going to be going into your sheet. Any comments, any questions about the general lighting? The general lighting? Adam, does it make sense? Brian? Yes, no? Karen? Okay. So that's your general lighting. Let's go to the show window. Can you guys see how you do the math for the two and you choose the largest? Now, Derek in 2014, they will allow you to use the smallest, but we're not in 2014. Show window. What did we say the show window was on my sheet? Adam, help me here. Show window was 2.5. Show window was at 2.5 here. For show window, I have 40 feet of show window, guys. 40 feet. Multiply every foot by 200 volt amp from the MEC code book. 200 volt amp. And multiply everything by 1.25. Why 1.25? Because it's continuous. And that will get you 10 kVA. Done. 220.43A. If you don't believe Brian that this is what you do, go to 220.43. We'll tell you to do it this way. Okay, track lights. Where do we have track lights on our track lights? Is 2.4. Track lights is 2.4 here. Okay, for track lights 220.43B. If you guys go there, it will tell you for every 2 feet, give it 150. Okay, I have 100 feet divided by 2, then multiply it by 150. What does that mean? For every 2 feet, give it 150. So you take the 100, divide it by 2, multiply it by 150. Don't forget to multiply by 1.25. Why? Because continuous load. That will get you 9 kVA. 9 kVA. So that's your track light. Your sign. Sign is 2.5. How does that? Can't be. Track light. Show window. I'm sorry. Show window was 2.6. That makes sense. No, this was 2.6. And then the sign was, I'm looking at the wrong sign, and outline light is 2.5. This is a 2.5 in your sheet. Okay, so for the sign, from 220.14F and 600.5, these are the code, guys. It will tell you we have one sign for a commercial building. It's going to be given 1200 volt amp from the MEC code book, and multiply it by 1.25 because it's continuous load. It's going to give you 1.5 kVA. That's your light. Parking lot. Your parking lot is 2.7 here. 2.7. That's your parking lot. 2.7, guys. It's actual, basically, because we have no idea. So I have 6 fixtures. Each one of them, when we ask Karen to design it, she threw 400 volt amp metal halide, volt amp, 6 of them in the parking lot, multiplied by 1.25 because it's always light. Brian, right is always continuous load. That's why we add 25% to them. This is equivalent to 3, they do the math right? Yeah, 3 kVA. 3 kVA allocated to the parking lot light. Allocated to the parking lot light. By the way, Derek, 2.8 in this sheet will multiply everything, add them up, and multiply them by 1.25. I'm not doing step 2.8, guys. If you look at 2.8, 2.8 is taking adding them all up and multiplying them by 1.25. I just did the 1.25 directly into every step. That's actually easier. Okay, any comments, guys? Any questions? These are all the lights. Different type of lights. Any questions? Any comments? Make sense? No? Yes? Too much? Too little? Okay, so that's your light. Then all lights, then you're going to add them up. Adding them up, that will be equivalent to 2.8. This is 2.8, 2.8. Can you please write this in a note? Please. At this step, 2.8, do not multiply by 1.25 because we already did that. So we just add them up. Here we add all of them up. So we're going to be adding all these steps up. So that will be, when you go there, 219 plus K, all these are Ks, plus 10K, plus 9K, plus 1.5K plus 3K. And if you did your math right, 242.5 kVA is your total. That's the one step that you're going to carry all the way through. All the way through for the lights. Almost there. Can you guys do me a favor when you're done here? I want to go just get, see that these stars that I did here? I want to go get rid of them. Anybody knows why? Because we already carried this number through. I don't want to confuse you. So can you guys go to step number 2.2 here and just get rid of the stars next to it? Because I already added them. I don't want to carry them twice. So I did add all the lights in one big fat step, basically. All the lights, one big fat step. Any questions? So now I have a lighting load and a receptacle load already done. The lighting load and the receptacle load already done. Any comments, any questions, guys, before I move into C? Let's go to C. C as the heating. The heating, guys, this is in my calculation, the heating was 4. This was 4 here. And the cooling was 4.1. This is 4.1. These are the two steps. Okay, and choose the largest and choose non-coincidental load is 4.2. This is a 4.2. This is correlated to the sheet that you guys have. Non-coincidental load, basically. All right, so let's go do that. Heating. For heating, I have 3 heaters. We asked Brian to design this building, and he decided to burn electricity. He put 3 heaters. Each one of them is 15 kVA. 15 kVA. And that'll get you a total of 45 kVA. Then we asked Karen to design the chillers. She went and she used 3 chillers. Each one of these chillers was 82 amps. And they're burning at 208. And they are burning also at 1.73. Divide this by, don't forget, by 1,000. And that will get you an 89 kVA for the chiller. 89 kVA for the chiller. Why did I divide by 1,000? Because everything we're adding is in a
Is that 1.73?
1.73. Yep. 1.73. 1.73. Anybody knows why we divide by 1,000? Because when you find the volt amp, it has to be kVA. We're adding everything in kVA. Then step 4.2, guys, says NEC 220.60. These are simultaneously used. Choose the largest of heat and cool, and it doesn't take much to figure out that 89 kVA is your largest load of these 2 steps. That's 4.2. Step 4.2 in your calculation. Step 4.2 in your calculation. Any comments? Any questions? Any comments? Does it make sense? If you guys designed your Excel sheet, that's probably you already did that. I can't emphasize the reason why I do this one for 2 reasons. Number one, because in Excel sheet, guys, it doesn't show the math on it when I give you the PDF file. I talked about it, but this at least shows you what the math that you need to do in Excel sheet. If you type an Excel sheet without math, do not give it to me. It's not worth it. I mean, I can't type it. I need you guys to put the math into it. Okay, shall we move to D? Motors? Yes, no, Karen? Good? Ryan? Okay. D is motors. So for motors, I have step 4.4. This will be 4.4. 4.4 here for motors. Okay, for motors, here's what I have. Motors. I have air handling unit. for air handling unit, guys, I have 20 horsepower, at 208 three-phase. That's what I'm giving, and I believe I have two of them. Two air handling units. Okay? So if you take the 20 horsepower, you go to 430.250. This is 250. Under 208, because the system is 208, it will give you 59.4 amps. 59.4 amps. I want to remind you, I have two of these babies. Two of them. Then you pick the largest motor out of the two. The largest motor out of these two. And then you do this math. You're going to do the following. 1.25 times 59.4 times 208 times 1.73 divided by 1,000. Don't forget 1,000. That's the largest motor plus all the other motors, which is only one more. 59.4 times 208 times 1.73 divided by 1,000. When you do this step, your answer should be 48 kVA for this step. Well, the reason why I did it twice because I need to add 25% on that guy. How are you going to do that? See, there's two motors. You pick the largest. There's also motors here, but this is 10 horsepower. This is 20. Definitely, these are the largest. So what I did at first, I did the kVA for the first motor, add 25% on it, and then added it to the second one. That's using the largest motor. For the pumps, we have, for pumps, guys, I have also two pumps, two of them, 10 horsepower each. So when you do the pumps, you take the 10 horsepower, take it to the same table, guys, table 430.250 under 208, and that will get you a healthy 30.8 amps. And then, since there's two of them, I take the two, multiply it by 30.8, multiply by 208 times 1.73, divide everything by 1,000, don't forget that, and that will give me the total for all these two together, which gets me 22 kVA. 22 kVA. Any question why I multiplied here by 2? Because there's two of them. Do I need to do them separately? No. Why did I do the top one separately? Math, because one of them I want to use as the largest. I will increase it by 25%. Then the total for the motor, you just add these two numbers together. You take the 48K plus the 22K. That will get you a healthy 70 kVA. This is the demand for this step. This is the demand for this step. Total demand for this step. We have one more type of load, guys, before we start sizing. Any comments, any questions? This is for the motor load. Brian, makes sense? No? Would you guys be able to do that on a test? Knowing that you can bring as many information as you want as long as you don't bring the example with you. Why did I do this step this way? Because I need to add 25% on the largest motor. Okay. Now, oops, not this one. The last step, guys, is E, the kitchen. For the kitchen, I have 3. This will be in your sheet, 3. When you guys go to your sheet, this is equivalent to 3. Kitchen equipment. Okay, let's go look at the kitchen equipment that we have. For a commercial building, we have the following kitchen equipment, guys. I have 3 water heaters. Each one of them is 5K. And I have 3 dishwashers, 2K. And I have 3 ranges, commercial building, 10K. And I have heater booster, 3 of them. Each one of them is also 3K. And when you guys do the math on this, it will get you 5K here, 5K, VA. This is, oh, I didn't do, no, we're not gonna. So when you do the math on these, do all this math and add them up at the bottom. When you add them up, you're going to end up with 60 kVA all together added. Quick reminder, I need to put some voltages here. This is 3-phase, this load is 3-phase 208. This phase load is 208. Oops. So I'm just putting the phases because it helps us size the neutral. This is single phase 208. The rest of them are single phase, and all of them are 208. 208, 208. Can you guys see how they're running them? They're running, the range is also single phase. They're running them, guys, 1, 2, 3. They're running these loads as single phase. These loads are running as single phase. And the top one, the water heaters, are running as 3-phase. How do you get single phase 208? You take just 2 hots. That's all. If you take 3 hots 208, that's 3-phase. Okay. Add them up 60. Then it says demand. You need to demand this step. The equipment from 220 to 56, the demand for 12 equipments, these are 12 equipments here. There's 12 equipments, right? 1, 2, 3, 4 times 3, 12 equipments. You go to 220 to 56, Karen, and get your demand factor of 65%. Then you take your 60, multiply it by 0.65, and that will get you a healthy 39 kVMA. That's the one that you're going to carry downstream. Ignore this one. I'll come to this. Can you guys see that graphic here? I will come to it when we size the neutral. When we size the neutral. So that's it. So these are all the chunk of the loads, 5 types of loads that we have in this building. Now we're going to go size the buildings. 5 types of load that we have in these buildings. Any comments, guys? Any questions? Would that help you guys understand the Excel sheet a little bit more that you have? I think the demand, I don't know that step for kitchen equipment. Kitchen equipment 220 to 56. Yeah, number 3. So there's a demand factor for the kitchen equipment. Any comments, any questions from this table? Okay, so let's go start sizing. I'll come back to that graphic in a second. All right, you guys have this sheet in the front of you. I'm going to go fill this sheet. I'm going to tell you why I'm going to fill this sheet. Everybody has this sheet, right? You guys should have this sheet. Now, let me walk you through what this sheet means. This is for all the A, B, C, D, E steps that we did, which is basically the receptacle, the lighting, heating, cooling, motors, and kitchen equipment. 5 types of loads. How are these 5 types of load are going to fit under the service panel, the receptacle panel, the lighting panel, mechanical panel? How are they going to fit? You have to you guys have 3 of them, right? Instead of 4, you have 3 of them for you in your sheet. Okay, so let's go ahead and for the receptacle panel, which color I'm going to use? 56 point, the phase is going to be 56.9 and the neutral is 56.9. Why do you think the neutral and the phase are the same when it comes to the lighting? Because all the lighting that we have, guys, are 120. All your lighting is 120. Okay, so that's light. I'm sorry, these are receptacles. Now, do me a favor. So this is the service panel, will see that load. Which other panel, Derek, will see the load too? The service panel, these are receptacles. Where are you going to feed them from? The receptacle panel. So this will be also 56.9 here and 56.9 here. And what do you guys think here? There will be 0 here, 0 here, 0 here, and 0 here. One more time. Let me repeat myself. We will have a 56.9. These are the receptacle demand load from the step A, all the step A that we did, guys. Under the phases, the same value will be for the neutral because all the receptacle loads are connected 120. They are neutral load. They will be seen by the service panel as well as the receptacle panel. Why do I put zeros for the lighting panel and the mechanical panel? Because they will not be fed from the mechanical panel or the lighting panel. Done. Can I have thumbs up, Chad? We understand why you did what you did. Cool? Okay. Now let's go to the lighting load. B is the lighting load, right? Isn't that what we said B is? B is my lighting load. For my lighting load, I have 242.5. Is that true? 242.5 for my lighting load. So for my lighting load, I'm taking this information, guys. I don't know if you. So this information is coming. I'm going back into my sheet. See what I mean? Going all the way back to receptacles and picking. Here's that 56.9 kVA. And so for lights, keep going all the way to lights. Here's that 242.5. 242.5. Okay? 242.5. So for lights, 242, I have 242.5, and the same thing, 242.5. 0 here, because that's line. This also will be 242.5 and 242.5, and 0 here and 0 here.
You got that little mixed up in there. The second one is RQ. You said 0 there because of light section or something.
This load is receptacle panel. I'm done with it. Okay. Lighting will be 0. When you go to the lighting load, B is a lighting load.
This is the light.
Yeah. B is A is the receptacle load, B is the lighting load. If you look at the type of load that we have. Okay. Any comments, any questions, guys? Why did we put the zeros under the other panels? Right? Because you're not going to be fit from it. Okay, moving on to C. What was C? C was the heating and cooling load. C was the heating and cooling load. For C, I have 89. We just did C. If you guys go back to C, C was 89. Can you guys see 89? Here's the C. C 89. So this will be an 89. 89 under the phase. How about the neutral? Hold your horses. Let's go back to the C. Step C and C. Is there anything connected on the neutral side? Derek, I have a 3-phase heating and a 3-phase chiller. That's about it. Is there anything single phase here? So what do you think the neutral would be? Big fat 0. The neutral would be, the load for the neutral really would be big fat 0. So this is this one will be 0 here because there's no neutral. On the receptacle panel, everything will be 0. On the lighting panel, everything will be 0. On the mechanical panel, because I want to feed these chillers from the mechanical panel. So what do you guys think on the mechanical panel? 89. And what do you think the neutral for the mechanical panel will be? Zero, because they're all three-phase. They will not contribute in any way, shape, or form for the neutral. This chunk of load anyway. C, let's go to D. D are motors. All my motors are three-phase. All my motors are three-phase. Can you guys see that? All my motors are three-phase. So if you go back to D, which was for motors, let's go back to D. Here's my D. Oops, D. Can you guys see all of them are three-phase motors? And the demand factor was 70 for them. So I'm going to go back here. For D, there were 70 here. 70. Adam, all of them are three-phase. What do you think I should put under the neutral? Big fat zero. They don't contribute. Will they be fit from the receptacle panel? I hope not. These are going to be motors from the mechanical panel. 0, 0. Derek, would I feed them from the lighting panel? No. 0, 0. Would I feed them from a mechanical panel? I hope so. So this will be what? 7, 0, and this will be 0. Any comments, any questions? Any comments, any questions? Does that make sense? Does that make sense? Okay. The last step is a little bit confusing for you. The last step is going to be, so are these, does it make sense, guys, how I allocate chunks of loads into different panels? Now, here's my question for you, Brian. If I don't have a mechanical panel, where would the mechanical load be fed from? It will be directly fed from the main panel. You just don't have a mechanical panel. Could I not have a mechanical panel like you guys? You don't have a mechanical panel. You have what? Main panel. All the mechanical equipment are fed directly from the main panel. Can I do this? Yes. What would it, if you do it this way, what's the advantage? You saved yourself one chunk of dollars. What's the disadvantage? You're putting all your eggs in one basket. When we design a building, as we chunk the loads. One chunk lighting, one chunk receptacles, one chunk mechanical. Okay, the last step is E. For E, I want you guys to, now E, the load for E was 39. 39. These are the kitchen equipment. How about the neutral? Oops. Thank you. Let's go back and look at E. See if we have a neutral. Here's the load under E. This one is three-phase. This one is, since this is three-phase, guys, drop it. These are single phases. Wait. How many of them do I have? I have 3 of each. If you have 3 of each, guys, single phase, you know what they do? They balance them. So they put one here, and one here. And when you balance them, they will show as what? 0. Yes, they are single phase. But because I have 3, so take, for example, the dryers. I will put one dryer here, the second here, and the third here. Between phase A and B, B and C, C and A. By doing it this way, you balance these dryers, and your neutral, you will not have a neutral load. That's probably the confusing part. So, and since there's 3, I picked them 3, by the way, for a reason. So they're balanced. If they're not balanced, then you just choose the one that doesn't balance. Yeah, because they're 3-phase, yes. Yes. What if they were 4 of these? Then the unbalanced one will be only 3 kW. One of them. That's the only thing that's going to be seen by the neutral. Yes, you can apply the demand. Yep. Exactly, you apply the demand. If it's more than 1. Yeah. Okay, so I hope I convinced you. These are balanced. So neutral-wise, for my neutral, this will be big fat 0. I don't want to. Now here's a question: where do you want to feed your kitchen equipment? You have a decision to make. Do I want to feed them from the receptacle panel? No, Chad, thank you. Do I want to feed them from the lighting panel? No, Chad, thank you. 0, 0. Do I want to feed them? Well, do I have any other option? Do you want to feed them from the mechanical panel? Yeah, they're kind of mechanical. So, but I could have said no, and I could have just left them on the main panel directly. But since I have an extra panel, I'm going to go throw them on the mechanical panel. Did I? Actually, I did not. In my case, I threw them in the receptacle panel. Don't ask me why, because they're not mechanical. So I put 0 here, 0 here, and again, believe me, it's a decision that you guys have to make. So I went and I threw them in the receptacle panel, right in here, for my example. 39, 39. I guess because they're going to be feeding receptacles, some of them, I put them on the receptacle panel. Could I have put them in the mechanical panel? Yes. But they're not really mechanical equipment though, so they are kitchen equipment. So I threw them in the mechanical panel. Okay. Any question, guys, about this sheet? I'm going to add them up and then give you a break before we size. Okay, so now add everything on every column. This column will have 497.6, 497.45. This is this column. Give me enough room here. So I'm trying to get myself. So 49.74. The neutral will be 299.4. 299.4 here. The second panel, it will be 95. I have 95.9. 95.9. For the neutral, it will be only 56.9. They're on balance. The second panel, guys, I have 242.5. 242.5. The neutral will also be 242, 242.5, all the lights. The last panel, I have 159K, all of them are K, and the neutral will be a big fat fluffy 0. Big fat fluffy 0. This is the load for all the neutral and the phases on this panel. The phases and the neutral in this panel, in these panels. Now I am ready to size. So I'm going to give you guys 5 minutes. Now I have the load. Before you leave, now I'm going to get these numbers and go size my panels on my conductors. Right? What we have done is load calculation. The next step is sizing. We're going to size the equipment. Just take 5 minutes. Right on the money here. Okay. Let's go back, guys. So here's all the sizes. So you know, this is equivalent. This sheet will be equivalent to sheet number 5. Number 5 in your sheet. So can you guys write? I don't know. We're gonna write this one 5 here. So that step in your sheet is equivalent to 5. Can you guys see 5? Where you do all the demand, all the load demand. Okay. So we got that. Now that we know all the sizes, we're going to go size the service panel. The first thing we need to do is size the service panel. So I'm going to go, guys, do the service panel. The first panel is the service panel. That's what we do. So receptacle, not receptacle, chair, go all the way to, we got that. Let's go to the service panel. Okay. So for my service panel, I want to bring to your attention, guys, if you go back, for the phases, the service panel load was 497.4, right? 45. So let's go get this number. So you're going to have 497.4 K. Divide this one by 208 times 1.73. Everybody knows why I said 1.73. That will get you 1,383 amps. That's how much amp your main panel is going to be sized for. That's
Where the 4K come from, sir?
the what?
4K. Oh, jeez, never mind. Okay.
497.4.
Yeah, I just put mine like in my head for whatever reason I saw 497 times 4K.
Yeah, 497.4 K.
Yeah.
All right, then you're going to take the 138.3 amps. You need to take it all the way to DeWalt. DeWalt, you guys should have DeWalt by now. 3-13, and that will get you a 1600 amp panel. So the panel size will be 1600 amp. And by the way, this is equivalent service equipment and sub panels. So equipment size. So that will be trying to see what's equivalent in that one. So we got the demand, total demand amps. The first step is 5 point total demand. Yeah, this is 5.2. This step is 5.2 in your book, in your calculation. That was 5.2. And then equipment sizing, service equipment and sub panel, and service equipment conductor. So 6.2. This is. So this is 5. I'm sorry. This is 5.2. 5.2 is this. This one is 6. This was 6 point, trying to correlate it with what we did here. 6.1. 6.1 right here. 6.1. So you know where we are in terms of the sheet that you guys have. Okay, the overcome protection device. The overcome protection device is the same thing, guys. You're going to take the 1383 amp, take them to 240.6, and I believe this should give you the same amps. This should give you 1600 amp. 1600 amp. So your panel, you guys remember what Todd says yesterday? The panel size is the size of the copper or aluminum inside the panel. The overcome protection device is the size of a circuit breaker ahead of it. Almost always they're the same, but they could be different too. So I have a 1600 amp circuit breaker. In our step, 240.6 equipment, so service equipment and sub panels. This is also in my step is also 6.1. These two are 6.1. I call them both of them. Cool. 6.1, 6.1. So you can correlate to what you're doing. Okay, moving on into the feeders. So service entrance conductor. For service entrance conductor, this is equivalent service entrance conductor. This is 6.2 in your sheet. This will be 6.2, the sheet that you guys have. Service entrance conductor match overcome protection device. That's it. You match the overcome protection device. That's how you do it. Okay, my overcome protection device, guys, was 1600. I have to parallel, so I'm running 4 sets. That will give me 400 amp. You're going to take this one to table 310.15 B16 under 75-degree column, and this will give you the following. I have 4 sets. Each set is going to have 3 conductors, and each conductor is going to be 600 kcm, and we're going to be using THHW. That's the size, the phase size of the service. 4 sets, 3 conductors in each set. Each set will have 3 conductors. Actually, I probably should have done it here, 400 amp. Take this one, I have step here to table 310.15 B16, have more room. So at 75-degree column, and that's where you get you the, I want to go here in parallel, just to make it organized a little bit, hopefully. So we're paralleling. We're paralleling. Everybody knows why we're paralleling, because we can't carry them. So I have 4 sets. Each set is going to have 3 conductors, because 3 phase, 600 kcm THHW. Why the W, not the N? Because if it's service conductor, most likely it's coming from outside. Outside is wet location, almost always. Okay, so that's my 6.2. Now let's go to the neutral. The neutral is also there's 6.2 here. This is also 6.2, the neutral. Service entrance conductor for the neutral. Okay, let's do the calculation for the neutral. I want to remind you guys the neutral load. Let's just go back and look at the neutral load that you guys calculated. There you go. Can you guys see the neutral load? 299.4. So that's the number they're going to use. 299.4. Okay. So I'm going to use neutral load of 299.4 divided by, I'm sorry, 0.8. gonna fight over 299.8K. Divide this one by 1.73 times 208. You're going to end up with a healthy 833 amps. That's your neutral amps. That's the amps for your neutral. Any comments, guys? Any questions about the amps for your neutral? Everybody got that? Okay. Now, the neutral, you're allowed to derate anything higher than 200 amp. The code allows you to derate for neutral anything higher than 200 amp. That's from 220.61b. In order to understand the code, guys, and be proficient, my expectation from you is every time I have a code reference, you should go in the NEC code book and highlight it. Otherwise, you're going to forget it. So, now, if you guys go to 220.61b, it will tell you that you can derate. So you're going to use 833 amps. You're going to derate. So the first 200 amp shall not be touched. Anything higher than 100 amp, 200 amp, which is 833 minus 200, the code allow you to chop them by, multiply them by 0.7. And then add. See what I did, guys? The first 200 amp, leave them alone. Anything higher than 200, cut it by 0.7, add them up. You end up with 643 amps of neutral load. 643 amps of neutral load. 643 amps of neutral load. Why do I derate? Because the NEC code book 220.61b tells you to go ahead and derate, no problem. Okay, now, Karen, because I paralleled 4 sets of phases, I must parallel 4 sets of neutral. I have no choice. So I'm going to take my 643. Now, here's my question for Adam. Do I have a choice other than paralleling by 4? I don't have a choice. I can't parallel 3 or 5. I have to put 4. Why 4? Because the phases are 4. I need one with every phase. So that will get me, when you do the math, it will get you 161 amp. And then you take the 161 amp, take it to table 310.15 D16 under 75-degree column. And that will get you Celsius. That will get you 4 sets. 4 sets of 1 conductor. Each one of them is 2 watt. 2 watt AWG THHW. 4 sets. Okay. Now, when you parallel, Karen, if you end up with less than 1 watt, you cannot parallel less than 1 watt. If you came up with number 3 or number 1, you have to up it to 1 watt anyway. You cannot parallel less than 1 watt. The code says so. Okay. Any comments, guys? Any questions about the service? I have my neutral and I have my phases. Here's how it's going to look like, guys. If you this is my phase A, B, C, and neutral in every set. Can you guys see that? And they tie them at both ends. Every phase at both ends. I have 4 conduits. Can you guys see the 4 conduits thing there? And right here, I have 4 sets. I have 3 conductors of 600 kcm THHW and 1 conductor 2 watt AWG THHN. So that's, see that 4 conduits, how it look like? Each conduit has 3 phases and a neutral in it. 3 phase and a neutral. Okay. Any comments, guys? Any questions before I move next? Matt, good? Okay. Main bonding jumper. You need to, everybody knows where the main bonding jumper is, guys. That's the one, go to the first page. That's the one, number 5. Number 5. Main bonding jumper tying the neutral to the ground. The main bonding jumper, if you guys go to 250.28D and 250.66, it will tell you to do the following. It will tell you to do the following. Since I have 4 sets, multiply the 4 sets by 600 kcm, that will get you 2400 kcm. Then 2400 kcm is more than 1100 kcm. The answer for this is yes. If that calculation more than 1100 kcm, then you have to do the following. Then you have to take 12.5% multiplied by 2400, and that will get you a healthy 300 kcm. And you take the 300 kcm, take it to chapter number 9, table number 8, and that will get you one conductor 300 kcm, THH, well this one THHN or THHW or bare. This conductor can be anything you want it to be. Let's say THHN because it's inside the enclosure. But really could be also bare conductor. I can't emphasize, let's say it also can be bare. Right? Because that's bonding the ground to the neutral. One more time. You take the number of runs multiplied by the size of the phases, get you a number. Check. Is this number larger than 1100 kcm? Then you have to take 12.5%. How do you convert this one, guys, into math? So you don't get confused. This is equivalent to 0.125 times. Everybody understand that? When you do your math.
What about if it was less than?
If it's less, then you use this number. And we go directly into chapter 9. If it's less, then you use that number and you go directly to chapter 9.
So that was just a created bare table or just bare table?
It could be covered, bare, or insulated. This is a bonding conductor. Bonding conductor, guys, can be covered, bare, or insulated. Most likely it will be insulated, though. It's not carrying current. Any comments, guys, about the main bonding jumper? The grounding electrode conductor, that's number 6. Everybody knows that these numbers correlate to the diagram that you guys have at the beginning too, right? The same calculation, guys, happened to the grounding electrode conductor. 4 times 600 kcm equal 2400 kcm. For this guy, you don't have to do anything. You take the 2400 kcm, take it to table 250.66. I'm sorry, Derek. If it's less than 1100 kcm, then you go to table 250.66 actually. And if you go there, it will tell you one conductor and a 3-aught AWG. It could be bare, covered, or THHW. Bare, covered, or THHW. One conductor. For the ground, everybody knows what the grounding electrode conductor, that's the one that goes from the panel into the ground rod or the steel of the building or the water. You do not need to do 12.5%. Did you guys hear me? No need to do 12.5%. Let me repeat myself because Derek, I think I told you wrong here. If that number was less than 1100 kcm, then you go to 250.66. Then you go to 250.66. Please highlight the tables. Please know how to use them, guys. We're going to be using them for this project, the next project, and every project if you stay in this industry. So these tables are used all the time. Okay, now we're done with the service panel. So what I did, guys, just quick all the way, let's go back all the way to that mess here. Okay, so what I did, Karen, is I sized the main panel. I sized the service conductors, including the neutral. I sized the main bonding jumper, and I sized the grounding electrode conductor, which is basically number 1, number 2, number 3, number 4, number 5, and number 6. Can you guys see that? I sized them for the main panel. Would you guys be able to size them for our? By Friday, you guys are gonna do that for me for the hour panel that we have. Not a big deal. You already have the sizes. Okay, so now we're gonna go size it for the 3 other panels. There are 3 other panels with it. So let's go all the way to. We got that one, main bonding, grounding. Okay, receptacle panel. Let's go to the receptacle panel. For the receptacle panel, Karen, I'm going to remind you, go back all the way to the load, guys. Do you see what the receptacle panel load is? 95.9 and 56.9, neutral and phase, okay? These are the numbers I'm going to be using. Okay, let's go all the way to receptacle panel. For receptacle panel, so we got that, receptacle panel. So the receptacle load was 95.9 on this panel, divided by 1.73 times 208, because it's a 3-phase system. That will get you a healthy 267 amps. I need to go size my panel, so I take 267 amps, take it to DeWalt, page 3-12. Please get DeWalt. If you don't have DeWalt, guys, in the test this time, no excuse. You got to have DeWalt book. 3-12, and it will tell you this panel is 300 amp. That's the copper inside the panel. Now I need the circuit breaker. Remember when Todd was here and he was showing you the main circuit breaker inside or outside the panel? Now we're going to size the circuit breaker. The circuit breaker, guys, is almost the same thing. Overclock protection device, except you go to 240.6. So I have 267 amp. Take this baby to 240.6. That's where we go, and that will tell you it's a 300 amp panel. It is a 300 amp receptacle panel. 300 amp receptacle panel. You know what, Derek? Almost always when you guys walk into any commercial building, you can almost guess. It will be one panel lighting, at least one or multiple 225 amp panel lighting, and another 225 amp panel receptacle. If you need more than 225 amp panels, they start adding more panels. It's not a good idea to go too much like 600 amp receptacle panel. Bad idea. So they go in chunks of 225 in real life. 225, 225, 225. If it's more than 225, they split them into 2 panels. Okay, so I have 300 amp panel, not far away from the truth for my receptacle panel. Now let's go to the feeder. The feeder conductor, we need to size the feeders. For the feeders, conductor spares 240.4B, that's a feeder. Okay, so we got that one. We got the feeder. Okay, so I can go 267 amp. My overcurrent protection device, overcurrent protection device, remember, was 300 amp. Now, here's what the code allows you to do, and here's what you should do. The code allows you guys to size your conductor based on, because this is less than 800 amps, the code allows you to size the conductor based on 267. Not a good idea. Match over current protection device. So I think, so that's what the code allows you. So good design is always match over current protection device. Match over current protection device. So what's the over current protection device? I have 300 amp. Take it to table 310.15 B16 under 75 under 75 degree column. That will get you the following, gentlemen, ladies and gentlemen. One set of what? 3 conductors, was 3 phase. Each one of them is 350 kcm. Most likely will be THHN. Why do you think, Derek, it's THHN? We're inside the building, right? So I have one set of conductor 350. One set. What's a set? A conduit with 3 conductors in it. That's a set. What happened to the neutral? Well, let's go size the neutral. Any comments, guys, about the receptacle panel? Any comments about your receptacle panel? Let me know when I can move. Karen, Brian, good? Okay. So let's go to the receptacle panel. For the neutral, guys, I can use 220. This is my 220. 220.61. Okay, so the neutral, here's my neutral load, 56.9 K. Remember that coming from my load calculation. Divide by 1.73 times 208. Why do you think we treat it as a 3-phase the neutral? Because it will be divided between the 3 phases, right? That will give me 158 amps. Now, 158 amps less than 200 amp. Then, do I have to derate? No. Remember how we derated 70%, guys? I have an 158 amps less than 200 amps. Do I need to multiply it by 0.7 like we did before? No, it's less than 200, so leave it alone. I'm going to say here, no derating. No derating 70%. No derating. Why no derating? Because it's less. Oh, what am I doing here? Am I doing it this way? Chad. It's less. 158 amps is less than 200. I did it. Wrote it the opposite. 158 amps is less than 200. Okay? Then, gentlemen, you're going to take 158 amps. You're going to take it to table 310.15 B16, 75-degree column. You're going to have, again, one set of one conductor, 2-aught AWG THHN. One set of conductor. So this conduit, guys, that you're going to have a conduit like this. Inside the conduit, there will be phase A, there will be phase B, and there will be phase C, and there will be a neutral. That's what you're sizing. Phase A, phase B, and phase C. The phase A, B, and C was 350, right? We had 350. And the neutral is 2-aught. My neutral is 2-aught. Okay. Any question, guys, before I move into the equipment grounding conductor? Equipment grounding conductor. Now, if you're using EMT conduit, you don't need an equipment grounding conductor or rigid. If you're not using an EMT conduit, you need an equipment grounding conductor. A lot of engineers, guys, when they use an EMT conduit, they like also with feeders to pull an equipment grounding conductor with it. So equipment grounding conductor, very easy, guys. 250.122, 250.122 cable. So that's very, very easy. You're going to take the overcurrent protection device equal 300 amp. You take the 300 amp to table 250.1, 2, and 2, and that will get you a healthy one conductor number 4 AWG THHN. So if you're pulling it inside the conduit, guys, it will be insulated. Do I need the equipment grounding conductor if I'm running EMT conduit or rigid? Do I need it? No. Do I need it if I'm running PVC? Yes. So going back, so let me just, I didn't, okay. So let me just draw the conduit one more time here because I like to draw. Here's my conductor phase A, here's my phase B, here's my phase C, and here's my neutral, and here's my ground. So this will be phase A, phase B, phase C, neutral, and ground, all in one conduit. What type of conduit do you guys want to make it? EMT. EMT. What size conduit? What size conduit EMT? You guys want to be sizing it, right? What size conduit? I'm going to size it only for this calculation, then let you go on that. I'm going to go use my calculator. I suggest that you guys will buy this calculator. It's really great, great asset for that. So I need somebody, size, picture, medium. Okay, do me a favor. Let's go set this one to 3-phase. Set 3-phase. I have 350, right? Isn't that what we have? Yeah, 350. Here's how do you do it. 350, the 3-phase, 350, and it's a K and a wire size. Copper, I have 3 of them. It's THHN, and click here. Here's the 3-phase. Then I have a neutral. What was my neutral size? 2 watt. Here's a 1 and a 2. Here's a wire size. How many neutral? 1, and it's the same thing, THHN. Then a ground. My ground was 4. Here's my 4. Wire size. How many of them do I have? I have 1. What insulation? I'm using THHN, same thing. This is my total. Can you guys see that? All my total. That's a cubic in square inch. And then you go right to the conduit and it gets you 2.5 EMT conduit. Right here, 2.5 EMT conduit. Cool? Now you guys have this calculator, you can use it on the test too, or you don't, you're going to go use the calculation. So 2.5 EMT. So this conduit will be 2.5 inch EMT conduit. You guys will be sizing it for my project, for the project, your project, not mine, your project. Okay, 2.5. I'm not asking to size these for this example, but for the test, you're going to do it. Okay, moving into lighting panel. Let's go to do the same thing. Now Karen, we're repeating ourselves, right? We did the receptacle panel and the main panel. Now we're going to do a lighting panel. Can you guys see a trend of repeating itself? Okay, receptacle panel, lighting panel. The load for the lighting panel was 242.5 K. The same voltage, 1.73 times 208. That will get you 674 amps. You take your 674 amps, take it to DeWalt, page 3-13. That will get you an 800 amp. My panel is 800 amp. Then the overcap protection device, guys, you take the 674 amps. Now we're going to take it to 240.6, and that will get us a 700 amp. Now, Derek, I want you to look at this. I have a panel, copper, inside the 800 amp, and an overcap protection device to protect the 700 amp. Is that okay? Yep, no problem. Could I have gone to an 800 amp circuit breaker? Yes. What's wrong with that? You need more money, number one, and more money both for the receptacle, for the circuit breaker, as well as for the cable. Okay, so the size of my panel. Now, based on the code, Karen, the size of your panel is 700 amp. The size of your panel is the size of the overcurrent protection device. That's what the code says. Based on the equipment, the size of your panel is 800 amp. You buy an 800 amp panel with a main of 700. That's how you do it. But when you go through the code, the size of the panel always goes by the size of the overcap protection device. No, so if they ask you based on the code, what size panel do you have? 700 amp, right? That's what decide, because the overcap protection device rules. But in real life equipment, what equipment did you buy? I bought an 800 amp panel with a 700 amp main. Okay, now let's go size the feeders, will you? Let's go size the feeders, the ungrounded conductors. So we got these, my friends, feeders. So number 3, I have my current was 674 amps. My over current protection device, I always say, guys, match over current protection device, even though you don't have to, which was 700 amp. So I take my 700 amp divided by 2 because I'm on a parallel. I have 350 amp. Then you take the 350 amp, take it to table 310.15B16 under 75-degree column, and that'll get you a healthy 2 sets of the following: 3 conductors. Each one of these conductors 500 kcm THHN. That's the size of your conductors. 2 sets. You almost could have now, Brian, you can, based on the code, size your conductor based on the 674. Remember, we're engineers. We go a little bit above the code. So it's always good to match the overcome protection device. Match the overcome protection device, especially on panels. Matt, can I move to the next one? Yes, no? Okay. Adam, we're good? Okay. Now let's go to the neutral. Now for my neutral, guys, my neutral, I have to go, I will remind you the neutral load was 242.5, so the same amount. It was 242.5K divided by 1.73 times 208 equal, the same calculation, 674 amps. Now, I want to remind you, 220.61B, this is, I believe, B here, tells you can derate the neutral if it's more than 600 amp, more than 200 amp. So then you take the 674 amps, guys, and do the rating. The following: 200 amp shall not be touched. Then, so you take the 674 minus 200, and you cut them by 0.7, and then you add them up, and gentlemen, that will get you 532 amps. 532 amps. Now you're going to hear, guys, if you have harmonic loads, you have full neutral and blah blah blah. So you can always pull full neutral. If you see your company pulling full neutral for these, that's because they're worried about the harmonics. Okay. Now, that's my neutral. Since then, I take the 532 amps divided by 2. Why divide by 2? I already, guys, parallel 2 sets for the phases. I must parallel 2 sets for the neutral. That will give me 266 amps. Then you take your 266 amps, take them to table 310.15B16, 75-degree column. And gentlemen and ladies, they'll give you 2 sets of 1 conductor at 300 kcm THHN. Guys, let me give you a disclaimer. Karen, you never pull a 700 amp lighting panel. That's way too much lights in one area. Way too much light. Did you guys hear me? That's theoretical value. In real life, if you exceed a 225 amp panel, it's very, very, very recommended to split them into multiple panels. So in real life, the 700 amp, what do? Chop them by half and run 2 350 amp panels. Or maybe chop them by 3 even and run 200 amp panels or 225 amp panels.
Even if you went just a little bit over 225.
Well, like we can push it to 300 amp panels. You'll see that 300 amp panels. You start going higher than 300 amp panels is not a good idea. Do you guys know why? 1 second, Adam. You know why? Because imagine these are lights. So in order to have a 300 amp at 28120, that's a lot of lights. You're going to have a voltage drop problem pulling all these branch circuits from everywhere. It's like the whole, the two floors going to the same panel. What's the issue? Well, there's nothing wrong with that except voltage drop. You start encountering a lot of voltage drop issues. That's why we see that panel here. They put a panel here, load everything here, put it on this panel. Done. Another for colleges. Another, every room almost have its own panel, and grab all these loads, put them in one panel, shoot them all the way down to the basement for voltage drop issues. So, reminder, 225 amp panels, your max up to 300, okay, don't go higher than that. If you need, cut and do multiple panels. Yes, sir.
I'm talking, but I don't think Halford's coming.
I don't think so, yeah. I don't know.
They said they were gonna be here.
Yeah, I heard guys saying they're not coming.
Yeah, he said they're gonna come like 2 or 3 weeks or something.
Okay, not a big deal. I'm entertaining you, aren't I, guys? Do I need to dance here and do other things?
I wanna recall it.
I want to
We
see
fu-
dance.
See that. Okay, here's my neutral.
Yeah.
Here's my dancing. So guys, the last thing I want to do is the equivalent grounding conductor for this baby. For your equivalent grounding conductor, I have a 700, I don't know if you guys can see here. I have a 700 amp, 220. You take the 700 amp to 250.122. That will get you a healthy one conductor, and it's a one conductor, 1 aught. Okay, one conductor, 1 aught, number one conductor, 1 aught, AWG. This could be there, but we're going to use THHN. So that's for my ground. Then, this is how your system is going to look like when you draw them. You have 2 sets, guys. I have 3 phase, phase A, phase B, phase C, each one of them, and I have a neutral and ground. So right next to here, this is how it's going to go. 2 sets of, that's how you guys going to write it for me on your schedule. 2 sets of, let's go. 3 conductors, number 500 kcm. 1 conductor, and these are THHN, of course. 1 conductor, 300 kcm, THHN, and 1 conductor, 1 aught, AWG, THHN. Gentlemen, this is what an engineer and a designer will write the feeder. You have 2 sets. Each set will have 5 conductors inside that set. Let's go size that conduit, will ya? Shall we see what size conduit we can do? That's a bonus. Let's go do the conduit sizing, since it's easier to do it with the calculator. I'm almost done, guys. 1 more panel left, and then we're done. Since Hallberg is not here, we can abuse the time a little bit. Okay, so I'm going to go set myself on 3 phase. Here's set. This is my 3 phase. Okay, let's go ahead. I have a 500. Can you guys see how you put it? You type 500 and you hit K because it's K, and you hit the wire. That's it. So that's 500 kcm. How many of them do I have? I have 3. What insulation? THHN. And you click, this is the square inch, the area of these 3 conductors, 500 kcm. Then I'm going to go to the second set. The second, I have 300, a K, and a wire size. That's a 300. What did I say here? Okay, 300. Okay, that's why. 300 K wire size. Yep. How many of them do I have? I have 1. What insulation? THHN. Click again. There you go. Here's your total, the 2 of them. The last one is 1 aught. 1 aught, you put 0, guys. Wire size, how many of them do I have? I have only 1. What insulation? THHN. Here's the cross-section area for 1. Here's the total cross-section area. And ladies and gentlemen, you click on this and your conduit size is 3 inch. Everyone can see that? That's my conduit size. So I'm going to use a 3 inch. So this is going to be a 3 inch EMT. conduit. Why am I pulling an equipment running conductor with EMT conduits? Better protection. Do you need to? No. Do you need to know? All right, let's go to the last one, shall we? Last calculation. Almost there. Okay, last calculation, mechanical panel. Let's go, gentlemen, to the mechanical panel. The mechanical panel, that's the HVAC equipment was on it. I have 100, for mechanical panel, guys, I have 159K. Divide this by 1.73 times 208. That will give me a healthy 442 amps. 442 amps. You're going to take your 442 amps. You're going to take this one to DeWalt 3-12, and that will get you a 600 amp panel. 600 amp panel. You're going to take the overcap protection device. You're going to take the 442 amps. Take this one into 240.6 from the sequence book. That will get you 450 amps. I have a panel the panel is rated for 600 amp, but the overcap protection device is 450. Now here's an engineering judgment for you. Some engineers will say, maybe I should drop my overcap protection device down to 400, and I use a 400 amp panel. It will be cheaper. You can't do that. If you're an engineer, you can. As a registered engineer, guys, I can sign off on anything as long as my neck is on the line and I can lose my license if it doesn't work. Would it work? Absolutely. If you go drop that 450 into 400 amp panel and put a 400 amp panel here, would it work? Absolutely. It will. But what happens if it doesn't work? And they go hire you as a registered engineer to review my work, and you see me dropping 50 amps below, I lose the case in a court of law. Definitely. You can see how we kind of designed to make sure that we cover all the unexpected issues. So 450. So what size panel, Brian, do we have here? It's not a 600 amp code-wise, it's 450. Okay? In real life and material-wise, it's 600 amp panel with a 450 circuit breaker ahead of it. Okay, so let's go size the conductors, gentlemen and ladies. So I'm going to go size my conductors, and my conductor have to match, I call match overcurrent protection device. Do you have to match the overcurrent protection device? No. Up to 800 amp, your overcurrent protection device can match your load amp, but always match the overcurrent protection device as a designer. 350. So we take the 350, gentlemen.
450.
I think I was drunk when I wrote this one. 450 amp cable 310.15 D16 under 75-degree column. You're going to have how many sets? One set of how many conductors? One conductor. And we're going to, oh, I made a mistake here. Was it 350? I sized this one wrong too. Ouch. You know what? This is too much. I need you to help me here with that one, guys. Let's take the 450 and parallel. Divide by 2. That'll give you 225, right? 225 amp, right? Am I right? Right? Then I'm going to go take 225 amp. Let's go parallel. Take to table 310.15 B16 under 75-degree column. Is that 4-aught?
Yeah.
Thank you. 4-aught. I thought so. That will be two sets of 4-aught. This is the 4-aught. Two sets of 3 conductors. Each one of them is number 4-aught AWG THHN. Gentlemen, you got yourself your mechanical panel size. Your mechanical panel size. Okay, now what's with the neutral? What's with the neutral, right? Let's go to the neutral. When we say the neutral, guys, I for the neutral was 0, divide by 1.73 times 208. That'll get you a big fat 0. So here's a big thing you have to do. I want to be, so no neutral. You can say we don't need a neutral, but that's a major decision. If you don't bring a neutral to a panel, guess what's going to happen? You can't feed anything from line to neutral. So you have two options, either no neutral conductor. That's one option. That's not what I want to do though. I want to pull a neutral. So here's what I would do, Chad Curry's opinion here. I would size a neutral based on a phase. This is kind of anecdotal type of calculation. In reality, I can make a decision, no neutral, and move on. I just don't want to pull a neutral. I don't want neutral in this panel. It's not a good idea, guys. If it's a grounded system, pull a neutral. So what size neutral do you need? I go back into the size of the, you guys, the assumption. We're gonna make a big assumption. My assumption is I'm gonna use this amount of amps, 442 amps. You guys know where this is coming from? This is for the three-phase load. I'm gonna use this to size my neutral. You know, I just want to use this to size my neutral, so I can have a neutral for this panel. Then, instead of 0, then you take the 442 amps. You need to apply the rules of the rating on it, guys. The first 200, leave them alone. Anything higher than 200, 442 minus 200 times 0.7, and add them up. This should add up to 370. 370 amp. 370 amp. Don't forget to add. So that's a decision you guys are going to do as an engineer. Say, well, should I pull a neutral? There's nothing connected, but what happened in the future? Now remember, guys, you're designing a system for 40 to 50 years. In the future, could they pull a neutral and pull neutral load? Yes. So that's how we do it. Okay, so any comments, guys, about this one? See my assumption, anecdotal assumption. Then, number 4, gentlemen. So I got my neutral. Continue with number 4. Then I can use, yes, I did divide this one by 2. What was the number that I came up with? 3. Okay, let me just see one more second here. So I have 370. I need you guys to help me here. So 370. 370 divide by 2, will you? Because I have to parallel.
185.
Thank you. 185 amps. Okay. Then, then you take the 185 amp to table 310.15 B16 75-degree column. That'll get you 2 sets. 2 sets of one conductor. What size? 4-aught. Are you sure? 185 amp. Wire size. I have 3-aught.
Yeah.
3-aught. Sorry, 3-aught. So one conductor number 3-aught AWG Now a quick reminder, Karen, if your conductor here was less than 1-aught, you must use 1-aught. So here's my neutral. Again, I can't emphasize that step is my opinion. When you guys go in the industry, if you have a panel, grounded panel, it's really nice to have a neutral there. So in the future, they can pull maybe neutral loads or what's not. But it's an opinion. Okay, the last thing, gentlemen, the last thing is the equipment grounded conductor. Good idea to always pull an equipment grounded conductor. So we got that one, equipment grounded conductor 250. So go get me, the overcap protection device is 450 amp. Take this one to 250.122. I don't have that one. Oh, I have number 2. this will be now. Did we parallel here? We did parallel, didn't we here? So this one is no longer applied. I need to redraw this. This will no longer apply because we parallel. So, and I need to do this one because guys, so the conductor 450, that will get you, you need two sets of one conductor, number what? Number 2, AWG THHN. Yeah, can you parallel? These are not parallel. Equipment grounded conductor, guys, they're not really in parallel here. Can be put in parallel sets if they're less than 2 watts. So I want to draw the circle here and size the conduit, and then we're done. Here's my conduit number 1. Here's my conduit number 2. Here's my conductor. Here's phase A. Here's phase B. Here's phase B. There's also phase B in this conduit. Let's go to phase C in each one of these conduits. And let's go to the neutral. Here's my neutral. And here's my neutral. And here's my equipment grounding conductor 2. And here's my equipment grounding conductor. So I have phase A, phase B, phase C, and neutral, and a ground. Same thing here, phase A, B, C, neutral, and ground. Let me size the conduit and we'll call it a day. Let's go size the conduit for this. Oops, right here. Okay, so help me with the size of the conduit here, please. Okay, let's go to the medium. So, what was the size of the phases that we came up with? Derek, what size phase? I don't have. So far. Okay. Let's go that one. So, okay, where am I here? Okay, so the phases was 4 aught, right? So let's go sit myself here at doesn't matter here, 75. Okay, so it's a 4 aught. 1, 2, 3. Wire size. How many of them do I have with the 4 aught? Was that the neutral or the phase? Feeder conductor. Okay, that's a feeder. You're right. So 4 aught. Oh, that's 3, Chad, not 4. Clean, 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 clean. So 4 aught. 1, 2, 3, 4. There you go. 4. Wire size. How many of them? 3. THHN. Okay. THHN. Then, what was the neutral?
3 aught.
Was the neutral 3 aught? Okay, 3 aught. 1, 2, 3. 3. And wire size. And how many of them do I have? 1. THH in every set. Okay. And then what was the ground?
That was 2.
Number 2? Number 2. 2. Wire size. And number 1. And THHN. This is my total. I hope I did it right. And here's my conduit size. Number 2. 2.5. So my conduit, gentlemen, ladies and gentlemen, would be number 2. So 2.5. So this will be 2.5 inch EMT. 2.5 inch EMT. Any comments, any questions? I hope I didn't click on the wrong button here. Any comments, guys, any questions? I hope by this example, going over this example, guys, I will PDF this one, put it in a network. As you build your Excel sheet, if you're stuck with any one of these, by the way, everybody knows how to relate the last steps into the equipment grounding conductor and grounding electric conductor way at the bottom. These are step 6. So that will help you guys build the math into your sheet. Brian, are we okay? Good? Can I have thumbs up? Kieran? Good? Derek? Matt? Adam? Good. Okay, thank you. Let me PDF the one for you guys and then we'll go from there.